China's expressway network now runs about 199,000 kilometers, nearly 5 trips around the Earth. That alone is hard to grasp. What is even stranger is that some of the road material behind this network is no longer just the old mix of fresh stone and oil, but steel waste once treated like an ugly problem with nowhere to go. Stay with me, and by the end you'll see how China turned part of that waste into a tougher road material, why some engineers think it could change the old asphalt recipe for good, and why some of these new mixes can even help close tiny cracks before they grow. If this kind of deep engineering story is your thing, feel free to like and subscribe, because this channel lives in the place where huge industrial problems quietly turn into breakthroughs. For more than 100 years, road building followed a simple formula: crush rock, heat bitumen, which is the sticky black part of oil, mix everything together, spread it, roll it flat, let traffic take over. It worked well enough that most of the world stopped asking if the recipe itself was outdated. The road looked strong, so people assumed the story ended there. It did not. The trouble with ordinary asphalt starts on day one. Heat softens it. Cold makes it stiff and easier to crack. Rain slips into tiny openings. Sunlight slowly ages the binder. Heavy trucks press down on the same wheel paths thousands of times until the surface begins to sag. A rut is just a groove worn into the road by repeated traffic, like a thumb pressed into warm clay again and again. The road that looks solid from a passing car is actually under attack every hour. That attack becomes a national headache in a country as large as China. The nation has built the biggest expressway system on Earth, and every kilometer has to be paved, checked, repaired, resurfaced, and paid for. At the same time, China is also the world's largest steel producer. In 2024 alone, it made about 1,005.1 million tons of crude steel, more than half of global output. Great roads on one side, huge steel waste streams on the other. The obvious question was sitting in plain sight. That waste is called steel slag. Steel slag is the rocky leftover from steelmaking, the hard crust that remains after molten metal is refined inside giant furnaces. Most people would look at it and see a dirty byproduct. Road engineers saw something else. They saw a material with weight, hardness, rough texture, and minerals that could do useful work. In other words, they saw a waste product that might already have some of the traits a road needs most. But turning waste into a safe road material was not simple at all. For a long time, the hard part was trust. Roads are not allowed to fail quietly. If a bridge wall cracks, people notice. If a runway deforms, planes notice. If a highway surface breaks under fast traffic, everybody notices. So no engineer could just dump steel slag into asphalt and hope for the best. The material had to prove that it could handle load, heat, water, freezing weather, and years of pounding from tires. It also had to prove it would not swell, break apart, or create new problems that were worse than the old ones. That proof did not come from one flashy lab demo. It came slowly, over decades. One key early example was Tianjin Port Second Road, which became the first road in China to use steel slag as roadbed fill in 1980. The road section was 2.42 kilometers long. When survey data checked it again in 2005, the cement road surface was still intact except for some damage at expansion joints. That is a long test in the real world, not a slogan, not a concept drawing, a real road doing a real job for decades. Then the story moved from roadbed fill to the pavement itself. In 1997, China built its first steel slag asphalt concrete pavement in Shanghai. That line matters because it means the slag was no longer sitting underneath the road, hidden out of sight. It was part of the road surface system that actually takes traffic. Later reviews said that despite heavy traffic loads, that pavement maintained good performance over the years. Once engineers saw that, the question changed. It was no longer, can this material survive at all? It became, how far can this go? More projects followed. In 2003, the Baoxi section of the Wuhan Expressway used steel slag and asphalt concrete ramps, and after 6 years of service, the pavement was still reported to be in excellent condition. In 2009, Beijing used 1,275 tons of steel slag asphalt mix during the renovation of Chang'an Avenue, one of the country's most visible roads. In 2011, the first steel slag asphalt concrete pavement in Xinjiang was laid at the S114 interchange in Urumqi, where it showed good smoothness, good resistance to water, and good skid resistance. This was no longer a one-city experiment. So why did steel slag keep surviving these tests? The answer starts with shape and texture. Natural stone used in road mixes can be strong, but steel slag often has a rougher outer surface and more sharp angles. That helps the asphalt binder cling to it better. Binder is the glue of the mix, the sticky part that holds the stone together. When the particles are rough, the glue gets more places to grab. Think of trying to stick tape to smooth glass versus rough cardboard. One gives the adhesive a lot more to hold on to. Density matters too. Steel slag is heavy and tough, which helps it carry load. In a pavement, load is not just the weight of one truck. It is the repeated punishment of many trucks, many days, many seasons, all hitting the same narrow paths over and over. A good road mix has to resist getting pushed out of shape when it is hot. This is why engineers care so much about high-temperature stability, which is just a formal way of asking one simple question. When the road gets hot and traffic gets heavy, does it stay flat? Chinese researchers started testing this with real numbers. In a 2022 study from Chang'an University, engineers replaced part of the natural aggregate in asphalt mix with steel slag. They found a strong result when 60% of one key stone fraction was replaced. The dynamic stability of the pavement mix rose from 3,947 to 5,732, which meant the road resisted high-temperature deformation much better. That was a 45.2% jump. In plain English, the mix stood up far better when heat and wheel pressure tried to push it into ruts. That improvement makes sense if you think of the road mix like a pile of objects under pressure. Ordinary rounded material behaves a little like a basket of smooth marbles. Under force, the pieces want to slide. Steel slag is more like rough puzzle pieces or broken brick edges pressing into each other. They lock harder, they move less. That does not make the road immortal, nothing does. But it changes how quickly the surface loses shape, and that can mean fewer repairs, longer life, and better performance on busy freight routes. Up to this point, the story is already impressive. China found a way to use a steelmaking byproduct as part of a stronger road mix. But this is where the story becomes much more interesting, because steel slag does more than help a road stay firm in heat. Its internal structure and mineral content also affect the way it handles energy. Some of the iron-rich parts inside steel slag can absorb microwave or induction energy and turn it into heat. That opens the door to a second breakthrough, helping asphalt heal tiny damage before it becomes visible failure. Self-healing sounds like a word borrowed from science fiction, so it helps to strip it down. Asphalt already has a small natural ability to recover if it gets warm enough. A microcrack is a crack so tiny you may not even see it. If the binder around that crack softens slightly, it can flow back together and reduce the damage. It is a little like warm candle wax closing a thin line that looked permanent when cold. The problem is that ordinary roads do not do this well enough, fast enough, or often enough to stop bigger failure. That is why Chinese research teams began looking at mixes that could respond better to heating. One 2023 study tested steel slag powder as a replacement for limestone powder in asphalt mixtures. The idea was simple but clever. If the powder inside the asphalt could trap microwave energy better, the material would heat faster and heal better. The results were striking. Depending on the mix ratio, some steel slag asphalt mortars rose from about 30 degrees Celsius to 67.4, 88.2, and even 103.8 degrees Celsius, with much faster heating rates than standard material. The same study also found clear healing gains. When conventional filler was partly replaced with steel slag powder, the healing index improved by 8.7%, 17.3%, 22.1%, 26.9%, and 27.7% across different replacement levels. The best gains came near the higher end. What makes that possible is the porous inner structure of steel slag. Porous just means full of tiny holes, like the little pockets inside a sponge. Microwave energy enters, bounces around, loses itself inside the material, and turns into heat instead of escaping so quickly. That is the hidden trick. Steel slag behaves a bit like an energy trap built into the road. Under the right treatment, it warms the binder around it from within. That warmth gives the asphalt a chance to flow back into tiny damaged spaces before they grow. Another study connected to Chang'an University found that steel slag had strong microwave absorption ability, and that its use could greatly improve high-temperature stability in asphalt mixtures, especially around a 60% replacement level in one key aggregate range. So the material was doing two jobs at once. This changes the whole idea of maintenance. Today, road crews often wait until damage becomes obvious enough to justify patching. By then, the crack is no longer tiny. Water has entered. Freeze and thaw may have widened the gap. Traffic has hammered the weak spot again and again. But a heat-responsive mix points to a different future. Instead of waiting for the wound to open, engineers can target the surface earlier, add energy in a controlled way, soften the binder, and help the road close small damage before it becomes a pothole. What happens when that idea scales up? The answer depends on who is doing the work, and in China the list is serious. Chang'an University in Xi'an has published major studies on thermal behavior, microwave absorption, and steel slag asphalt performance. Wuhan University of Technology has worked with Wuhan Iron and Steel Metal Resources on experimental road sections using steel slag asphalt concrete. Reviews of the field also point to work linked to major steelmakers such as Baosteel and Shougang. This is not one professor running a lonely side project. It is a network of universities, materials experts, steel firms, and transport engineers all moving on the same question. Industry support matters because no breakthrough in road building lives on papers alone. It has to move into factories, mixers, trucks, and construction plans. Sinopec, one of China's biggest energy and chemicals companies, says it has developed special asphalt products for sea-crossing bridges, tunnels, high-viscosity paving, rubber asphalt, and hard-grade uses. Under its Donghai brand, it says it has taken part in more than 300 national key highways and urban roads and 17 national high-speed railways. That matters because it shows how large suppliers can turn niche material science into national supply. The numbers behind the bigger steel story are just as important. China's road system is vast, but so is its steel output. Steel slag often amounts to around 10 to 15% of crude steel production, depending on the process and plant. With China making over 1 billion tons of crude steel in 2024, even a cautious estimate points to enormous slag volumes. Some research has described the national steel slag total as well over 100 million tons a year. Once you see that, the road question changes again. This is not just about performance, it is about what to do with mountains of material. And this is where the credibility picture gets stronger. By 2018, Reuters reported that Ansteel had invested around 1 billion yuan in 8 slag processing lines. That is not the kind of money a giant company throws at a useless side issue. Around the same period, reports on Baosteel's environmental work said the company had spent 860 million yuan on a landfill and related plans tied to industrial waste control. The exact road formula may vary from place to place, but the message is clear. China's biggest steel players take slag management seriously because the scale is too large to ignore. Real-world proof matters more than budgets, though, and China's timeline is hard to dismiss. Tianjin Port Second Road opened in 1980 and still held up well decades later. Shanghai's first steel slag asphalt pavement went into service in 1997 and reportedly kept performing under heavy loads. The Wuhan expressway example from 2003 remained excellent after 6 years. Beijing's Chang'an Avenue used 1,275 tons of steel slag asphalt mix in 2009. Urumqi's S114 interchange followed in 2011. Step by step, the material kept moving from lab theory into roads that people actually drove on every day. One of the more telling examples came from Wuhan, where Wuhan Iron and Steel Metal Resources worked with Wuhan University of Technology on an experimental road section using steel slag asphalt concrete inside the company itself. That may sound small, but in engineering, these controlled test sections matter a lot. They allow teams to watch real wear, real weather, and real loading under conditions they can inspect closely. Every successful test section lowers the fear level. Every failure teaches where the limit is. That is how a risky material slowly becomes a standard material. If the material keeps proving itself, the next leap will not just be stronger roads, it will be smarter road care. One route is induction heating, which means using an electromagnetic field to create heat inside the material instead of blasting heat only from the outside. A simple comparison is an induction stove, where the pan heats directly instead of waiting for the air around it to do the job. For roads, that means tiny internal damage could one day be treated with more precision, more speed, and less waste than the old cut-and-patch method. That is a very different maintenance future. There is another branch of this idea too. Some studies around steel slag in pavement point to snow melting or faster heat gain in cold conditions. That matters in northern regions where winter safety is a constant battle. A material that responds to heat more efficiently can help the surface reach safer conditions sooner. It does not mean the road becomes a magic heated plate. But it does mean the same thermal behavior that helps healing can also support other functions. Once engineers see one useful trait, they start asking what else the material can do. This is why the phrase, "made asphalt obsolete," feels dramatic but not completely crazy. No, China did not erase black roads overnight, and no, every road in the country is not suddenly self-healing. What is becoming obsolete is the old idea that a road should be made the same way everywhere, from the same fresh materials, and then repaired only after visible damage appears. China is pushing a different model. Build with tougher recycled inputs, design for heat response, plan for targeted maintenance. Treat the road as an active material system, not just a flat black surface. That shift matters beyond China. Roads are not glamorous, but they are strategic. They move food, medicine, machines, power crews, freight, and people. They connect ports to factories and factories to markets. If one country finds a way to make roads last longer, use fewer virgin materials, and cut waste at the same time, that becomes an industrial advantage. It lowers long-term costs. It reduces pressure on quarries. It creates a new market for treated slag. And it tightens the link between steel production, waste management, and transport infrastructure in a way many countries have not yet matched. China has a special advantage here because the system lines up. It has giant steel output. It has giant road demand. It has universities studying pavement materials in depth. It has large, state-backed and private firms that can scale production quickly. And it has local governments able to try pilot sections in real cities under real traffic. That shortens the path from waste pile to research paper to test road to wider rollout. In some countries, those steps live in separate worlds. In China, they can sit almost next door to each other. That makes progress faster. Still, a balanced story has to say what could go wrong. Steel slag is not a miracle rock. One serious issue is chemical activity. Some forms of steel slag can expand if they are not aged, stabilized, or processed correctly. Expansion inside a road is bad news. It can create bulging, surface damage, and long-term instability. Reviews of the field even pointed to research showing that highly active slag could cause bulging under harsh conditions. So no responsible engineer treats raw slag like free gravel. It has to be prepared with care before it earns its place in a pavement. The same rough and porous structure that helps slag grip, binder, and absorb energy can also create downsides. A porous material tends to soak up more asphalt and can also affect water behavior inside the mix. If the design is not adjusted, the road may end up with less free binder where it needs it most. That can hurt water stability and low-temperature crack resistance. In simple terms, the material that helps in summer can become a problem in winter if the mix is pushed too far. That trade-off is one reason the research matters so much. The 2022 Chang'an University study makes that trade clear. It found strong gains in high-temperature stability, but it also showed weaker low-temperature performance as steel slag replacement climbed too high. In that study, replacement levels above 80% did not meet the standard requirement. That is a big warning sign. It tells engineers there is a useful window, not a free pass. Around 60% replacement in one part of the mix kept showing up as a sweet spot, but a sweet spot is not the same as a universal answer. Climate, traffic, and local materials still matter. Cost is another honest challenge. Some studies have noted that steel slag asphalt concrete can cost more at the start than ordinary asphalt concrete, in one case more than 30% higher. That extra cost comes from processing, transport, and the way slag's texture can demand more binder. For a mayor looking only at this year's budget, that number can look ugly. But first cost is only one layer of the math. If the pavement resists rutting better, lasts longer, and needs fewer heavy repairs, the lifetime cost picture can flip. Still, that payback has to be proven, not assumed. Environmental safety cannot be brushed aside either. People hear industrial waste in roads and immediately worry about toxins. That is a reasonable concern. Some forms of slag can contain trace metals, so researchers have to check leaching, which means whether chemicals can escape into water over time. This is the line between smart recycling and careless dumping. If the material is not treated and tested properly, public trust disappears fast. That is why standards, pre-treatment, and long-term monitoring are not boring side issues. They are the difference between a breakthrough and a mistake. There is also a practical operations problem. A road mix may be capable of heat-assisted healing, but that only matters if the maintenance system around it can actually use that capability. A city might lay advanced steel slag asphalt on a test section and then discover it has no good field process for induction or microwave treatment at scale. The material would then be smarter than the repair network meant to support it. In other words, the road and the maintenance tools have to evolve together. Otherwise, part of the benefit stays locked inside the chemistry instead of reaching the street. Public understanding matters too. Most drivers do not care about aggregate source, filler chemistry, or thermal response. They care whether the road is smooth, safe, and durable. If recycled steel slag pavement works perfectly, many people may never know it is there. That is probably the best outcome. The road should not feel experimental. It should feel boring in the best possible way. Quiet, stable, dry when it rains, flat when trucks pass. If it can do that while using less virgin stone and turning waste into value, then the material has already won its real argument. What makes this story powerful is that it is not just about one better road surface. It is about connecting industrial systems that used to be treated as separate. Steelmaking creates a byproduct. Road building needs huge volumes of hard material. Waste policy pushes companies to find better uses. Universities test the limits. Suppliers scale the best formulas. Cities provide real-world proof. Once those pieces lock together, the road stops being just a road. It becomes a place where energy, mining, heavy industry, transport, and environmental policy all meet. That is why this topic matters more than it first seems. And if the best version of this idea matures over the next decade, the effects could spread far beyond China. Heavy freight corridors could use mixes tuned for rut resistance in hot weather. Urban roads could be designed for quicker surface maintenance. Cold region highways could take advantage of better heat response. Countries with big steel sectors but strained raw material supplies may copy the model. The headline phrase about asphalt becoming obsolete may still be too blunt, but the deeper point holds. The old road recipe is being challenged by something smarter, more circular, and in some cases more repairable. That is also why so many outside observers miss the real story. They hear self-healing and think the claim is too big. They hear steel waste and think the material must be cheap and weak. But the deeper truth is almost the opposite. The hard part is not making a headline. The hard part is making a boring road that quietly performs better for years. China's steel slag work matters because it has kept moving in that direction through actual projects, named universities, measured performance, and long test records. The breakthrough is not fantasy. It is patience with numbers. Good engineering often looks like this. It begins with a problem nobody wants. A steel plant makes mountains of leftover slag. A highway network keeps aging under heat, rain, and truck weight. Someone notices that these are not two separate headaches. They are two halves of one possible answer. Then come the studies, the pilot roads, the arguments, the failures, the better formulas, and the slow climb from odd idea to accepted method. Years later, the result can look sudden from the outside, but from inside the work, it was built one test at a time. So, no, China did not kill asphalt in one dramatic stroke. It did something more serious. It exposed how old the usual road recipe has become. By using steel slag to strengthen pavement, improve heat response, and support self-healing behavior in some mixes, Chinese engineers are showing that the road of the future may still look black from above while being far smarter below the surface. That is the part that makes people stop and stare, not because it is loud, but because it quietly changes what a road can be. This whole story comes down to one idea. China looked at a giant waste stream and a giant infrastructure burden and asked whether one could help solve the other. The answer, step by step, has been yes. Not perfectly, not everywhere, and not without limits, but enough to make the old asphalt playbook look less like a rule and more like a habit that can be replaced. If you want more stories where hidden material science changes the shape of whole countries, hit like, subscribe, and turn on notifications so you catch the next one when it lands. And tell me in the comments this. If your country had to rebuild one major part of its infrastructure using recycled industrial waste, would you start with roads, railways, bridges, or ports? And what would make you trust that choice?